as early as the early 1900s, coal was identified in South Africa. And it was envisaged to essentially spur South Africa's industrialization. So it was acknowledged that you have this coal resource and you can burn it, it's energy. And this was around the early 1900s. So if you go to the Council of Geoscience portal, you can actually find some of these publications from the 1910s and 1920s, where they first identified the high-felt coal fields. So this is classically what we know to be the major of coal development. But when you read those reports, it's very curious, because the scientists actually say this is a resource that will probably drive the South Africa's economy and development. So yeah, that's quite important, right? So we now move several hundred years into the future, and we find that coal indeed was one of the key drivers of our economy. So at that stage, of course, a lot was not known about the potential impacts of climate change. And as we move forward, after a long-standing utilization of coal, we find that South Africa is recorded as the largest CO2 emitter on the African continent. And the government then joined, let's say, the global movement to try and combat climate change. And I think one of the key points was in 1997, when South Africa essentially ratified the United Nations Framework Convention on Climate Change, meaning acknowledging that climate change is a problem and we have to put in measures to reduce essentially atmospheric CO2. That's the principle. Further than that, that ultimately resulted in the Kyoto Protocol. So that was to say that countries will actually try to ensure CO2 emissions go down. That was very important. From that, because we knew we had a lot of coal, the country felt, well, we can't just shut coal off, so let's look at interventions. And one of the ways was, well, if CO2 is a problem in the atmosphere, let's not let it get into the atmosphere. So grab all the CO2 after you burn it and then do something with it. So curiously, CO2 is very important, right, because it has carbon. So CO2 is a carbon carrier, and you can actually use CO2 to make much petrochemicals from it. So you can make wax, you can make lots of butanes and ethanes and many different things from CO2. So the idea was, well, if we can capture the CO2, we can find a way, you can actually make an economy from it. And beyond that, you'll be able to essentially reach your climate change objectives. So in the early 2000s, that's when the initial study started to look at, can we capture the CO2 and can we store it somewhere underground so it doesn't go into the atmosphere? And that work ultimately resulted in South Africa developing the first atlas of carbon storage. So what this atlas said was, around the continent or the country, there are several sites where you could probably take the CO2 and stick it in the ground and it will stay there. The challenge with this atlas was that the CO2 storage sites were far removed from the emission sources. So the sites were located, for example, off the west coast and the east coast and the southern coast of South Africa. So targeting essentially shore basins and nearshore deep saline aquifers. And it was not economically viable to capture the CO2 in Mpumalanga and transport it all the way to the coast and stick it in the ground. The other problem was, if you know your geology, some of these areas are actually tectonically active. So we have the East African origin that disappears off into the Natal Basin, and this is not exactly a good site to pump CO2. In addition to that areas, there are lots of faults that are deemed active. So there was in the late 1800s, there was quite a big earthquake in St. Lucia, magnitude 7. So this is not exactly where you want to store CO2 in the ground, of course. So we had to relook at that. So sort of in 2009, a whole bunch of people come together, these are the emitters and science, and we decide, well, we need to now relook at how we do this. The World Bank came on board as well. So I can share that the World Bank actually funded this project, $23 million US. You know, nothing comes for free. Keep that in mind. It's not always as simple as it is. And essentially, the idea was to relook at carbon storage. Where else could you store CO2? So we decided to be a bit specific, and we felt that we will make CO2 storage onshore at the proximal sites of the emission work. And that's where this story kind of starts. Other things to note is that South African government has adopted a carbon tax in 2019. And according to the budget vote, if you watch that, carbon tax went up. So basically, if you emit CO2, you have to pay tax, essentially. And I don't know the number off the top of my head, but essentially it's charged per ton of CO2. So it's something about between 20 and 30 Rand per ton that a company must pay. So you can imagine if you're if your bottom line is not doing too well and you still have to pay a tax, especially if you're in the coal industry, this could essentially bankrupt you. So again, there's a lot of possibilities in terms of like trying to reduce those emissions. Essentially, we're right now, CGS did a geological characterization of a site in Mpumalanga, and this was adopted, meaning it was internationally approved. And if you look at the latest version of the IRP, which is essentially how the government plans to develop energy. So they talk of coal generation, nuclear, hydro. You now see in the IRP, it actually says that CCUS should be considered for further coal development. That was quite significant. That means in government policy, they've accepted that CCUS is a potential mechanism to reduce CO2 emissions. And the last point I mentioned here is that part of the study where also have to look at environmental aspects. So you might want to store CO2 underground. It goes up. So you have to do an entire environmental study to kind of confirm whether or not there would be negative impact in terms of storing CO2 underground. And I'm glad to report this study, we actually have environmental authorization. So where we are right now is we are essentially moving to the step of storing CO2 underground. Maybe we'll talk a bit more about that as well. So the site selection is quite important. So if you look at this, essentially, this is a small town of Leandro. I don't know if anybody knows Leandro, very tiny place. There is a KFC, so it's not too small. You can use that as a basis to see how big the town is. It's a tiny little town, not far from Gauteng, but this is a very good site, right? But essentially around Leandro, you have major coal-fired power plants. So this is sort of within a roughly 50-kilometer radius. You can see that we have Kusile, Kendal, Kriel over there. And importantly, to the south, we also have Sasol Secunda. So this is the second coal-to-liquid plant that was commissioned by Sasol. So what they do is that they coal and they convert it into a whole bunch of different waxes and chemicals and different petrochemicals. These are very important sites, right? Because this one little map ultimately contributes more than half of all the electricity to the country. This is very significant. So if you just want to turn off the power plants, then we don't have electricity. I think that's what it comes down to. Importantly, the Sasol Secunda site also produces a lot of petrochemicals like waxes. But more importantly, they also produce fertilizer material. So when the Russia-Ukraine war started, the fertilizer price went up. And to import fertilizer became quite expensive, and that meant food prices went up. So, local industries that start producing this type of fertilizer material become quite important. But similarly, the other important point here is that the Sasol Secunda site is also regarded as the single largest point source CO2 emitter in the world. So they emit approximately 50 million tons of CO2 per annum. So they take a lot of coal and they burn it and they produce all these nice things and they make tomatoes out of it, but they also emit a lot of CO2. So if you attach a carbon tax of between 20 to 30 rand per ton and you multiply it by 50 million tons per annum, it's a lot of money. And you know that, business is tough, these days. So it's not that, thing they're doing so well. So that's sort of the setting. The other important point to mention there is you'll notice on this map, I mentioned Evander. So that's a gold mine that's not far away. They need a lot of energy as well. So they're drawing down from CO2, drawing coal for energy as well. And they're using that for the mining production. And we are not also far from Gauteng. So there's a major, if you move towards Gauteng, my favorite place is called the Wild Triangle. So that's another little hub where you use another coal to make many, many things. So this is a very good site in terms of CO2 emissions. In addition to that, we must admit as well that because the long-standing mining has happened, the place does not necessarily have the best environmental conditions. Mine water drainage, lots of emissions, there's health issues, there's acid rain as well. So it often happens that the desulfurization filter on the coal-fired power plants malfunctions, and then you have acid rain falling down. So if you go to these areas, you find a lot of people are bald because of the acid rain. So this is also another issue to deal with. On this map, we'll show some data sets. So we collected a lot of data for this project. This blue block that you see around here, that was a high-resolution airborne geophysics survey that we've done. That's gravity, magnetics, and radiometrics at a line spacing of around 200 meters spacing. In addition to that, you see this little red block. That's where we've done a 3D seismic survey as well. This is also some 2D seismic lines, and you'll notice here the dots are basically boreholes that we have, so legacy boreholes. In this area, we're not showing it, but there's around 1,500 boreholes
And that's purely because of a mining industry. So keeping in mind, the mining started in this area within the last 100 years, beyond 100 years actually. So there was a lot of deep drilling for gold exploration, coal exploration, and platinum. So you might wonder, like the bushveld, but this is actually part of the Bethel lobe of the bushveld complex. So once you go down to something like 2,000 meters, you actually intersect the bushveld. But because of that, there's been a lot of exploration work. Unfortunately, we had access to 1,500 bolts, which was quite good. So that's the site. The other important thing that you have to remember is you do not do the science in isolation. So this falls within the government backing municipality. Essentially, their economy is almost entirely dictated by the mining value chain. So this off that you see here, between mining and manufacturing, that essentially links to the coal industry. So this is an entire local municipality that is completely dictated by coal. So you think about this as well, the government goes to the International Climate Change Commission, they make a decision, we're moving away from CO2, an interpretation comes up that banks can't fund coal projects anymore, then you kill essentially an entire economy of a municipality. So hence this type of science becomes important to find mechanisms to deal with that. In addition to that, the municipality has a development plan. So of course, the way things work, there's an election that happens, and there's a budget that goes down to municipalities, and the municipalities have to come up with ways to spend the money. So one of the mechanisms that they've looked at is to say, we want to sustainably use our coal resources. So they want to expand on converting coal to liquid. You'll notice now, if anybody has a car, your petrol price is going to shoot up very soon because of the war in Iran. So this is one of the reasons why they have this industry here, because during apartheid, we could not import coal. So they decided, let's try and convert this coal into a fuel source. And that's where this industry started. So you can see with IP like this that belongs to the country, you might want to consider how can that actually be used. And in addition, there's a lot of people, more than 10,000 people are employed by the mining industry. In addition to that, it's not just mining of coal mining, but there's also rehabilitation of coal mines. So once the mine has been closed, the area is rehabilitated and they try to convert that to an agricultural site. So meaning they start planting food and have maybe cows grazing. So it's quite a good area. Also to mention, unemployment rate is quite high. So they are facing a crisis. The youth unemployment in this area is up to 50% almost. And hence the development plan of the municipality to look at its natural resources for its development links to then producing jobs. So again, this becomes very important. We mentioned acid rain here, just some graphs. You can easily find this. So from satellite data, because South Africa is relatively well regulated, these emitters have to report their emissions. So we know when the emissions of CO2 and sulfur dioxide, so your SOx's and NOx's go up because it's reported. In fact, there was a famous line that reported that some of the coal-fired power plants were killing 2 people per day because of the CO2 levels were so high, because the desulfurization filter went offline, but the country needed energy, so they produced energy regardless. So it was quite curious, right? So energy is being produced by coal, so that policymakers that are living maybe in Cape Town are making decisions about moving away from coal. So again, there's a reality that we have to deal with, but essentially the air is not good. So there's also a benefit to extracting these type of gases from the atmosphere, so not letting it get into the atmosphere in the first place. So this is the geology. So here's the geological map. So in the area, we remove the roof and all that stuff. So we're not interested in the crew in this area. So when you look at the geological map, if you look at any geological map and you have to point to Leandro, you just see brown, which is the echo. So we were not interested in that. So this map removes all of that, and we're looking at the basement rock. So that's the Wits. So essentially, we are in the Evander basin of the Wits. That's what you're seeing on the map to your left. And the pink are basically all your Archean to paleoproterozoic granite domes. So the Joburg Dome. I think you guys go to the Joburg Dome for your one field trip. So essentially, we have the same type of dome in Leandro, in this area. And the yellows are all your Wits, and you can see there's a lot of fractures. And then as you move towards the south, you also have the Wits, or the bushveld further. So there's a cross section over there. So that's kind of what we're dealing with in terms of the geology. So another key point to mention, this actually sits on the contact between what we call in the Eswatini and the Witwatersrand block of the Kaap Operator. So this deep structure actually controls a lot of the stresses. So that will be important because I'll come back to the stress issue. But the other important thing is that there's a very significant array of faults as well. That also becomes important. Maybe just as a bit of a teaser, the faults control permeability that controls water in the area. So these are things to consider. If you store CO2 underground, does it get into groundwater? But essentially, that's the geology of the area. I just mentioned here that the stress regime as well, it's an extensional regime. So when you look at, this is also important because if you store things on the ground, you might have seismicity. So understanding the stress regime is important. So then we started looking at the stratigraphy. So these are some of the bones. And essentially, this is what we're dealing with in terms of the actual stratigraphy. So this is our site, Lebogango Leandro. And essentially, we find that we have two possible reservoir sequences on this map. So just to go through this, you have the Karoo on top. You have a little bit of the Pretoria of the Transvaal. Then you have the Dolomites. So the Mamani Dolomites. And then below that, you have the Ventersdorp supergroup, which is this massive basalt. And then below that, you have the Wits, so gold-bearing Wits. Coincidentally, I can share with you that when we looked at some of the data, we discovered that this area actually intersects some gold-bearing reefs. So this is gold-bearing reefs that, if you look at the depth, this is less than 2,000 meters deep. A lot of people are mining in Leandro, so this became another topic. Essentially, we are saying that in Leandro, you do have gold-bearing reefs that are currently mined in the West Rand and the East Rand, essentially, the equivalent, currently mined now at the current gold price. So this implies that this area becomes a little bit more valuable in terms of just saying, well, it's all about coal. That's quite important. What we also did was we sampled. So this yellow dots over here, that shows you where we sampled some of the bowls. So we sampled to look at, can we store CO2 in any of these rocks, essentially. There's some pictures of the core, and this is a stratigraphic log of Ventersdorp. So by looking at these rocks, we identified two plausible reservoirs. So firstly, we identified that we might have deep saline waters in the Wits. So that's important, right? So you know when they mine in the Wits, they have to pump all that water out. So that's deep saline waters that may be a possible source for storing CO2. And then another possible source was all this green stuff. So we identified that we have a huge, massive volume of this Ventersdorp lava. And essentially, it is plausible to store CO2 in basalt, and the CO2 mineralizes. So it gets captured. So that became our two hypotheses. We have two reservoirs, deep saline, and then basalt of the Ventersdorp. We did a lot of stuff. So we did logging. So I'm glad that I think we guys also do a lot of logging. So this is just a snapshot of some of the 1,500 balls that we had to log. And if you look at the, you might sort of just notice it. There are little red dots. So we essentially sampled the hell out of these balls. Because the point was that, this is a very new science that we're trying to implement. And it implied that we needed a lot of data. So we digested the right word to use a lot of these balls in terms of identifying possible pieces of evidence to store CO2 in it. A lot of stuff, but essentially we've done geochem, mineralogy, petrology. The interesting thing to note here is that this is now focused now on the basalt. So now this slide we're dealing with, can this basalt store CO2? So the first challenge that we were encompassed with, and it's the first question that people ask, aren't these rocks too old? Because one would assume that an old rock is highly altered. So any type of possible that would react with CO2 may not exist anymore. But if you look at the photomicrographs, we start seeing that we have these matrix silicate minerals. So there's insertypes. Basically, we have planetaraxene, autoparaxene. And as you move towards the bottom of the sequence, you start seeing very interesting alteration minerals. So what we learned from this is that as you go down the stratigraphy, once you get closer to the VCR or the contact reef, essentially, you get more fluids, and that starts to draw down the matrix silicate minerals. So this is very good. The lesson here is that actually the Earth was sequestering CO2 ultimately. The fluids that were moving through the rocks was actually enabling natural carbonation of those rocks. The other important thing I might want to mention here, just to make it very topical, is that we started seeing some other interesting things. So when you look at the concentration of cobalt, chrome, and nickel, it turns out these rocks have very high concentrations of these minerals. Now, these are deemed to be critical minerals. So a lot of those minerals are required by the global north to invest in weapons that they use to bomb other countries, right? This is a very important point. So, there's a movement towards critical minerals. A lot of the critical minerals are required for weapons. So this is also important. How does a country determine its critical mineral strategy? Do you want to import critical minerals that are used for weapons? So this is a way to also consider global peace. We discovered that our vessels were actually quite significant in terms of these type of minerals. So you would also know that the price of nickel has gone up, and it became plausible that you could actually extract the nickel while storing CO2 in those rocks. So the nickel is captured in mafic silicate minerals, and if you pump CO2 into these rocks, it breaks down the mafic silicate mineral and it releases the nickel, and we are able to extract that. So that also became quite important. But essentially, the point here was that the rocks don't look too bad. We did quite a lot of mineralogy. So this map just shows you primary minerals and secondary minerals. So the yellow are your primary minerals, and the green is your secondary minerals. An important thing to note here is that as you go down the stratigraphy, so you can see we're starting at 1,000 meters below the surface to maybe 1,700. You see that the greens get a bit darker. That means you get more alteration minerals as you go lower down the stratigraphy. What was good about this is that actually, as you go above the stratigraphy, there's not so much alteration minerals. So the take home from this is that you have a lot of rocks to potentially react CO2. I think that's the important message. We also have to now deal with some physical properties. So now that you have a lot of rock that can react CO2, but can the rock actually absorb CO2? Is there any porosity? Is there any permeability? So one of the things we did was micro CT scanning, micro CT scanning, and we found that we do have small pores. We also coupled this with things like helium picometry. So you basically take a piece of the rock and you stick it in a jar and you pump it full of helium, and you see how much helium gets into the rock. So we found that these rocks actually have a percent porosity. So that's sort of enough. It's quite low, but it's enough to really get some CO2 into the rocks. The other thing was, this is the geophysics. Sure what permeability. So now that you know the rock will technically absorb the CO2 through the 5%, if you can maximize it, you actually have to get the CO2 into the rock. So these rocks are not permeable, meaning they not have inherent permeability. We decided to target fractures. So essentially, we want to enhance the permeability through the inherent fractures. So using this airborne geophysics that we have collected, we were able to extract a lot of the structures. So the airborne geophysics was used to identify the surface expression of the structures, and then we used the 3D seismics to extract the 3D geometry of those structures. So what that basically means is you can kind of see this is just a slice of the 3D cube, and there's one of our boils that we've drilled. The first thing to note is that the 3D seismics goes down to around 4 kilometers, which is quite good. The other thing to note is because we had ball data, we could correlate observed structures from the seismic data to the ball data. The third thing was because we had airborne geophysics, we could see the extension of those structures. And of course, because of the 3D seismics, we could actually extract the 3D geometry. So that's quite important. So what we did was we identified some of the significant structures that we thought were quite critical for permeability, and we labeled them. And then we were able to extract the geometry relative to the stress regime. So what this thing actually shows is all of those structures, how do they relate to the underlying stress regime, and how can we then manipulate those structures to enhance the permeability without having any negative impacts? Those are what the structures. So here's a Morse diagram. Many of you guys do this stuff. This Morse good. So essentially, you know that the closer these dots are to the scalar envelope, the more critically stressed the user term they are. So what that basically means is there's our fractures plotted on the zero space. This little beach ball is the stress regime. So this tells you that most fractures in the area would reactivate as a normal fault. Essentially, that's what this beach ball means. And then when you plot these things onto a slip diagram, so these two diagrams are essentially the same almost as the Morse diagram. And where the things are red, it implies that those structures are more likely to slip. And then you can quantify that. So now we know that, these structures over there, which we can identify on the 3D seismics, are there. We know that they are essentially critically stressed, and then we can quantify that stresses with the Morse diagram. So we know that we can target, for example, these structures 4, 2, and 8, and we can cause them to essentially rupture at pressures of, we calculated this, roughly 5 megapascals above the port fluid pressure. So that's important. So what that means is when you want to pump your CO2, you can carefully pump the CO2 just at those pressures to enhance the permeability without causing any seismic activity. That's what it basically means. The other thing was, well, what happens once the CO2 is in the rock? So we simulated that. So there's various types of geochemical things that you can do. So we started to simulate. So we had the rock, we had the sample of the rock, we had the geochemistry of the rock. So we're able to take that information and then simulate that with different types of fluids. So what you're seeing here is just an example of how we simulate that. Essentially, all of those lines are your minerals. And the only important one I want to point you to is this purple line over here. So this purple line is basically calcium carbonate that starts getting formed. So you'll start to notice with these graphs, these other lines either stay flat or they start going down. So they represent each mafic silicate mineral in the rock. Right? So if the things start going down, that means the CO2 is starting to digest those minerals. But when you break down that mineral, you start to form another mineral. Essentially, that's where you start seeing things like this. So this scenario 2, and you can see we run the simulation for 1,000 days. So essentially, that's saying if we take this rock that we have, and we pump it full of CO2, and we leave it for 1,000 days, we're going to essentially start forming calcium carbonate dolomite. So that's quite important. That means your CO2 is gone. It basically dissolve the pyroxene and it makes a dolomite, essentially. That's what it means. The other important thing to note here is that storing CO2 underground requires a lot of water. So we used 4 scenarios for these simulations. We used normal drinking water, we used deep saline waters, we used raw mine water, and we used processed mine water. So the country spends roughly between 1 and 2 billion rand every year to remediate mine water. So when they pump all that mine water out, they have to process that and cost, well, taxpayer up to 2 billion rand per year. So we thought, well, can we then find a solution to this? So you might start thinking that, well, if you have a fluid that has maybe a little bit of sulfides in it, sulfur, we could technically start to form things like anchorite and siderite. Those are calcium carbonates that have sulfides and ions in their structure. And that's basically what we start. This was also quite promising. And I think the last thing that we did, I think this is the last slide, we then had to consider, well, what does this mean for the economics? So here we looked exclusively at coal. So we started at the beginning saying we need to reduce CO2, so let's cancel coal. So then hence we said, oh, okay, well, if we can reduce the CO2, then what does it mean for coal industry? Essentially what this graph means, we project up to 2050. So that's sort of generally a developmental time frame. And essentially what we learned from these, from this analysis, this goes back to the 1960s in terms of coal production. According to this models, we find that depending on your reference you cite, South Africa may have mined about around a third of its coal reserves. That's the first important thing. So we potentially have between 2/3 to a half of all our coal reserves. That's a lot of coal. That's the first thing we learned. The second thing we learned is actually the coal employment continues to grow. So every year we employ more people in the coal industry. And when you project it up to 2050, you can get up to between 140 to 160,000 people direct employment in the coal industry. That's another important point. The other thing we noticed, because of the nature of the IRP and how some of our coal-fired power plants are quite old, the CO2 emissions associated to coal, so coal fire, generally hovers around 200 million tons per annum. So South Africa emits roughly 500 million tons per annum CO2, and half of that comes from coal. So this is very important. The last thing we worked out was, well, how much money can you make? So if you project up to 2050, technically you could grow the coal industry up to nearly 500 billion rand per annum in revenue. And the last thing we did was, naturally, you might ask this question, well, how much space do you have in this one reservoir? So essentially you have roughly, we do not know the bottom of the Wits. I should mention that. According to 3D seismics, we think we're dealing with rocks that go down to about 4 kilometers. But if you look only at the basalt, there you have roughly about 300-meter thick rocks that extend for several square tens of kilometers. And if you look at the ratio of the mineral carbonation, it would seem that you're dealing with several gigatons storage potential. That's why it's significant. So that implies that this reservoir could theoretically sequester all of South Africa's CO2 emissions combined theoretically. But we don't have to stop there. So what do they do in the global north? It's good to learn from the global north. So in the global north, they do not store CO2 underground for free. So they assign a carbon trading scheme. So for every ton that you store CO2 underground, the government basically pays you. So you get a trading scheme. So the global average for CO2 trading is $50 per ton. So in South Africa, if you could store all of the CO2 in Leandra, you could create a emission trading scheme in government backing of more than $20 billion US dollars. So what the global north does is, if I have good rocks and somebody else emits CO2, they pay me $50 or €50 per ton, then I store CO2 underground. And that's how the funding mechanism works. So we thought, well, why can't we do that in South Africa? So what this essentially will propose is that instead of just having a carbon tax in South Africa, we may also propose having an emission trading scheme and then start making them global north, for example, pay for storing CO2 underground, and especially some of the high emitters. And yeah, we hope that one of the things that this will do is develop this emission trading scheme. So in terms of where we are right now with the project, we've concluded the geological characterization. We've had this sort of international review, especially through the World Bank. That's been approved. We've done a preliminary engineering design. Essentially, that is how would you design such a well to get the CO2 in the ground. We've done probabilistic seismic hazard. We've done environmental baseline. And currently, right now, we are planning, if all goes well with the funding, to essentially start developing this injection well. Hopefully, this calendar year, we hope it all goes according to plan. And essentially, this will be the first of its kind. So this will be the first, what you might want to call a dual reservoir underground carbon storage site in the African continent. And we hope then that will then start driving such an emission trading scheme, and we can start contributing to the economic and social development of the country. And I think that's all. Thank you.
Thank you. That was incredible. Most impressively, I think, and for the students and people online in the audience, an industry and a profession that's often got a negative perception, coal mining, mining in general, geoscience. Geoscience is actually contribute to the development of people and so I think that's a really important aspect of this book. I think it's a big one. Also shows how important that's really great. So, do we have any questions? We can start with
Taufeeq Dhansay here from the University of Pretoria. I think we've got several questions. Let's start with the which is obviously more or less giving us the ceiling. I mean, I think the modeling of that, should you guys have done it, and what are the numbers, and also, I mean, what is the potential for that? Of course, then we can play around with what is feasible. And two, when you're looking at the injection well, that you are going to be sinking, what is the maximum sphere of the injection that you can have until permeability becomes almost impossible, because then you would have to increase the amount of pressure that you're pumping with. And so what is that? And then finally, the geochemistry of it is that when you're looking at what the guys do, particularly where you've had these injection sites in the north, is that they typically have been associated with geothermal energy, which means that the permeability has been more or less geologically being certified or guaranteed. But with us, this is basically almost dormant structures. And when you then start pumping CO2 in there, what happens is, at first, obviously the CO2 sequestration, the CO2 critical condition exists at that pressure. It dissolves everything around, which is fantastic, and then it just can seep through everything. But then once you start having carbonates start precipitating, then the porosity starts dropping. As you have all of this, which is what you want, but after a while, each injection site will ultimately become dead, because porosity will drop down to almost nothing. And has that modeling been accounted for? That means how many injection sites would you then need in order to fully maximize the full capacity for CO2 sequestration?
So that's a good question. So the one project where they've done injection on a commercial scale in basalt is in Iceland, actually, Kopfix. So there's a curious thing about the Kopfix project. So they actually inject the CO2 into a volcano. So there's a volcano, and they extract the hot water from the volcano to produce heat. So they essentially run the hot water through essentially a heat transfer, and they take the heat and they use it for district heating. So the water that they extract from the volcano has a lot of CO2. So they separate the water to get the CO2 out, because it basically corrodes the pipes. And they use the cleaned water to then run the district scale heating. They then take the CO2 that they extracted from the volcano and they put it back into the same volcano they came from. So they're recycling the same CO2. I mean, that's a very important point, because essentially the geology is slightly different, but there's a good point. So what they've learned is that they do lots of vertical wells, and they're very small capacity around it, as you say. Our intention is to actually use horizontal drilling, so to maximize the permeability as much as possible. We're really fixated on the stress conditions, because essentially what we want to do is, for lack of better term, we want to frack the rocks. So we feel it is very plausible to frack the rocks in a very safe and sustainable manner if you've done the correct structural geology of the brittle tectonics of the rock. So our model is not to actually use vertical wells, but to use horizontal wells or deviated wells. So what you ultimately want to do is have one wellhead, have multiple horizontal wells going into the area, and then maximizing the permeability as much as possible. While we were there in Iceland, we also got Kopfix, the only, as I mentioned, the only company to have injected into salt, to actually run the numbers for us. So we felt it's very hard for us to say, oh, we have several gigatons. So their own model suggested if we can access roughly around 2% of the rock, we could get up to more than 30 gigatons. That is a significant volume. So we would have been happy with even 1 million tons. So this means in terms of how we develop the well, because this is the next key question. So in terms of running a pilot, you could technically, and this is what the concept was, develop the injection well and target an injection of maybe 10,000 tons of CO2. But that's a very big capex cost. So meaning bring a drill rig, drill the hole, and then pump 10,000 tons. That's like one of these trucks driving around, you see these trucks for the fuel. That's like one of those trucks. So the idea here is if we get this value chain going, the model would be not to just develop a pilot scale, but to develop a commercial scale. So actually then bring the right equipment to maximize the permeability. And the idea would be that we would then target at least up to several million tons for one drill. That would be the idea. So this is very technically challenging, but I think that's also the exciting part. Essentially, that comes down to how much we would then target to sequester the program.
Great question.
Hi, Taufeeq, that was great. Thanks. I wanted to ask did I hear the percent porosity was 5%? That seems quite low. And is it actually permeable? I mean, is the porosity connected? And as the minerals change, does that increase or decrease? So is it going to get clogged up? I mean, it's a similar question to what he was asking. But I wanted to ask, have any experiments from the rocks been done with this under proper pressure and temperature? And then also you mentioned the saline water, but didn't talk about that as, did I hear you mention that as a potential storage site? Okay, if you could clarify that too. Thanks.
I really forget about the saline waters, but yes. So below the Ventersdorp and into the Ventersdorp, you have the green rocks and you have the, what's basically. So the nature of the age of the rocks dictate that a lot of those structures are limited to those units because of the deformational history in the area. And what we've identified, especially in the Vander gold mines, when they intersect some of those structures, they intersect these saline waters. They've done some analysis on those waters and they find that these are confined aquifers where the water is basically 2 billion years old. So this is very positive for us. It implies that you have a pocket of fracture-hosted groundwater, very deep, that has been basically static for 2 billion years. So those are basically the saline waters we would want to target for injection, deep injection. In terms of the, let's say that, so that would follow, let's say, more conventional carbon storage, where the CO2 just stays in the water. This is not necessarily the most ideal scenario, because essentially if the ground burps, then the CO2 comes back up. So we found that there's been a lot of projects where they look at saline storage. Notably, there's one in North Africa that was called the Insala project, where they stored quite a large volume of CO2 in saline waters. And there was a major seismic, well, not a major, but minor seismic event. But it was enough just to open the permeability, and all that CO2 that you tried to put in the ground and just came back up. So that's not necessarily, technically viable. But the best thing to do is actually to clog the rocks up, as you're saying. So the more you clog the rocks, to use that term, the better, because that implies that your CO2 that you're injecting in the rocks are now converting into these carbonate minerals. So that's essentially what we want to create. And the good thing is, if you know that you're going to clog the rocks up, that's when you want to design the injection well accordingly. So theoretically, the way this would look is that you might have this well, and you drill horizontally, maximize the permeability, and you start injecting slowly so that you get the CO2 going up. What you might wonder, well, how do you monitor this? So with this, you can put down things like seismic monitoring. You can also do geophysics monitoring on the surface, because you would change essentially the resistivity of the fluid, and you can actually model the plume, where's it going. So you'd be able to see where exactly does the CO2 go. And then you can slowly start to monitor. So this is what they do in Iceland as well. So they found after 2 years, when they drilled into the rock, they found that the CO2 had basically mineralized. We will not have 2 years. That's because of the chemistry of the rock. So the K values, so meaning the ability of the minerals to be reactive, the kinetic value of the minerals, we do not have very fast minerals. So your things like olivine generally would be very fast to react to CO2, because we have pyroxenes, they're much slower. So coming back to Sue's last question, is that the best thing to do is then to test this. So we actually started an experiment 20 days ago, 21 days ago now, where we stuck some rock into a compressor, and we ramped up the pressure to the pressures we expect at the reservoir. We're running that at 37 degrees, because that's what we think the geothermal gradient is. And we're going to leave that rocks in that compressor for the next 2 months. And then we'll take it out, and then we'll see how much minerals formed, and also what minerals formed. And that's quite good. So we're going to play around with different fluids to kind of see what type of fluids can you work in. Does it have to be CO2 plus water? Can you use acid waters, etc.? But we're hoping that after 2 months we'll have some results on that.
All right, let's ask Lou to unmute and come through, Lou. Hopefully we can hear you.
Okay, can you hear me?
We can hear you in the front of the room, unfortunately, but we'll repeat the question for everyone in the
All
audience.
right. If you can hear me, my question is this. It seems like you have chosen the Ventersdorp as your target repository, but I noticed that there's also bushveld in the area. And I wonder why you're not considering bushveld. To me, it would seem like a very favorable target. More olivine, more mafic, maybe shallower. I don't know. What do you think?
So for those that didn't hear, the question is, there's bushveld in the area in addition to Ventersdorp. Obviously, there's much more olivine in the bushveld, so would you consider using the bushveld?
Thanks, Bruce. That's a good point. Yes, actually, 100%, we would consider that. In fact, that goes back to the question of the critical minerals. Because there's so much olivine, because it's much more reactive, the idea would be that, well, while storing CO2, let's actually extract some of those critical minerals. I probably should have mentioned that regionally, we do have this additional storage reservoirs. I guess the reason we showed this one in particular was simply because this is where we've done the integrated study in terms of looking at what is the likelihood of long-term mining and the environmental considerations, but Lou's 100% correct. And in fact, because of that point, we do not even have to limit it to the Ventersdorp, the bushveld. Essentially, from what we're learning, wherever you get these mafic silicate minerals, such as in mafic and ultramafic rocks, this becomes a viable storage reservoir for CO2. I think that's quite critical. So it also implies that you would not necessarily need a large-scale reservoir. You could actually have modular-style reservoirs right next to a carbon fire plant, essentially. The other thing, maybe just to mention, again, maybe going back to Lou just sparked this point, because you have such widespread geology, we're only dealing here with coal-fired power. But do not forget that there's also lots of CO2 associated with the cement industry, with the transport industry, and also things like petrochemical, addition to petrochemicals, but like steel manufacturing and ferrochrome smelting. So this implies that, you might take this modular approach as well of having smaller scale storage sites associated with these areas. But yeah, thanks.
Okay, great. And then I think we have one question from Nikki Wagner. Nikki, do you want to unmute and come through?
Hi, thanks for the opportunity. I just wanted a clarification on one point, Taufeeq. You mentioned that it's
Nikki, sorry, could you just speak up a little bit? We can't hear you very well on the speakers. Could be us, but maybe if you could just speak a bit louder.
Is this better?
No, but give us what, because we would like to all hear the question.
Okay, I can't do much. I'm on my iPad.
Second, here we go. No, I think we're okay.
Okay, can I try again?
That's better. There we go. Sorry.
Okay.
Perfect.
Just for clarity, Taufeeq, I heard you mention that this is going to be a dual injection system, injecting briny water as well as CO2. Did I misunderstand something?
So I implied the dual reservoir. So we might target multiple types of reservoirs in terms of a basalt and a deep saline reservoir. So the theory here is that based on the seismic data and the structural data, it would suggest that we have permeable zones that basically transcend both the Ventersdorp and the saline waters. And it implies that if we target those permeable zones, obviously carefully, we could actually get storage in both basalts and the deep saline waters. So that was sort of the dual.
Okay. And then, but then I was just wondering why, when you did the mineralization tests, that you used raw water, potable water, and so on. Why were you not testing with CO2 mixtures?
So we did. So all of those. So those are sort of the fluxes. So there's, I guess, two ways you can store the CO2. You can either mix it with water, or you can actually pump supercritical CO2 directly. The reason we used water as a fluid was because of the permeability. Because the permeability is lower, we would want to use a base fluid to enhance the permeability and then use that as a carrier for the CO2. The problem with the fluid, we didn't actually talk about this, is that according to the studies conducted in Iceland, the amount of water required is essentially 1 to 25. So that means 1 part CO2 to 25 parts water. That's quite a lot of water. So we thought that, well, we're not saying that's going to be the case for us, but that's essentially what the current international model would suggest. You can play around with that. In the US, they're also doing some injection into basalt, and there they don't use any water. They just use pure supercritical CO2. So we can play around with both. Now, the reason we played around with different types of waters was, that's quite a lot of water, 1 part CO2 to 25 parts water. So we thought, what are the possible water sources we might be able to get access to? So one of them is the deep saline waters. Another one is the raw mine water, and another one is the remediated mine water. What I can share with you actually from the findings, and I didn't touch on this, is that because the remediated mine water and sometimes the deep saline waters have a lot of cations and anions, that seems to accentuate mineralization as well. So essentially the cations and anions, allow precipitation around the structure. So that seems quite good, but yeah, essentially that's why we tested the different waters.
Yeah, there's one question at the back.
Afternoon, everyone. Arwani speaking here. I'm not sure if I missed it. Came in a bit late. Sorry. If you spoke about, okay, how I understand it is that you're pumping CO2 to sequester it or carbon capture it into the interest of lavas, right? And then you've got minerals, new minerals that form out of that. So in terms of the physical part that you then have because of those new minerals, did you then look at, or have you thought of the competence of the rocks now with those new minerals or pressures that they'll be able to withstand or not in cases of sinkholes and things of that sort? I know it's a bit deep, but did you think about that?
It's a really good question. So fortunately, we have both types of rock in this area. So the lowermost part of the Ventersdorp has already gone through natural carbonation. So here's a curious fact. If you look at the bottom part of the Ventersdorp, that was a tomatite. So it had a lot of olivine, and all you see now is a talc-rich rock and lots of dolomite as well. So those are secondary minerals that formed after the rock naturally broke down. So that gives us a proxy of what would happen in the long run. So of course, we're dealing here with billions of years, right? So we're able to then also model or actually test those rocks as well. So the same geotechnical studies we then conduct on those rocks. Fortunately, because it's so deep, you would not have that impact. But maybe the one thing I should mention here is in that lowermost rock, we found lots of ilmenites and magnetites. So this is something that we did not expect, but once you break down those mafic silicate minerals, you actually form hydrogen. So a lot of the so-called white hydrogen that's being discovered in Mpumalanga, we think is coming actually from carbonation of the lowermost Findersdorp. And if you look at the mineralogy, we had to do these geochemical models because I don't know thermal pulp, how to use it. So if you look at the mineralogy, then you can actually see that hydrogen would have been a significant byproduct of this.
Okay, great. Thank you. There's a few comments in the chat. If we have some time, just to maybe we can just look at a few of them. I think some of them are interesting, and maybe we can just do these two together. First is, where else has this been achieved in the world? I guess in South African context, are there regulations required for CO2 storage and well design?
Okay, so in terms of where it's been done, there's two big projects, or I should say two prominent projects. The one is in Iceland, where they've stored the CO2 into the basalts. Very different basalts, very young. Minerals are slightly different, they have more olivine, but there they've stored, I think, just more than 100,000 tons of CO2. The way the Iceland project works, maybe economically while I'm on it, is that they actually they have a big project that does direct air capture. Right, so they have these fans next to the volcano, and the fans suck the volcanic air and then separates the CO2. And then also when they separate the CO2 from the volcanic waters for district scale heating, that's how they then get the CO2 that they put underground. They then charge a premium on that CO2 to the European countries. So for example, you might find that some of the countries want to reduce the CO2 emissions. So then Iceland sells the amount of CO2 they're pumping underground as carbon credits, essentially. So that's the one model. The other project, and then just to keep in mind, that's the one that uses water. So 1 part CO2 to 25 parts water. In terms of the water, they use glacial water. So because they're glaciers, but then somebody discovered that obviously glacial water is drinkable water. But they're now actually using seawater, which is quite mind-blowing. The assumption was that seawater would be essentially, that they would have too much salts essentially, and it would not actually enable mineralization. But according to their studies, they're able to use seawater instead of glacial water. So that's the one project. That's probably the biggest project currently. There is another project in the US. It's in Washington, if I'm not mistaken. That's a bit different. Their volumes are quite lower. However, they use pure CO2, so they do not have to use water. And then there's some other projects. So there's a few projects in India, naturally, because they have the Deccan Traps, so they have a lot of basalt, and they have a lot of CO2 as well, because they have a big coal industry. And then there's a few other projects as well that's doing experimental work in Australia and somewhere in the Far East as well. So fortunately, there's quite a number being done.
Okay, and I think there's one last comment about future mining in the area. How, I guess it's the interplay between storage of the CO2 and mining, future mining, for instance, gold, coal, and the leakage and other aspects around that interplay.
Yeah, we think, I don't know if it's we or me in this one, maybe it's me. So because there's deep coal seams, the suggestion from my side would be to gasify those coal seams. So drill into coal seams, gasify it, extract syngas, and then pump CO2 into the gasified layer. This is being successfully conducted in Ermelo, actually. It's one of the global projects where they successfully conducted underground gasification. So we think based on the structures and based on the geology, we could get away with that. So that's one aspect. A lot of the reason I mentioned that is the easily economically mineable coal seams appear to have already been exhausted in this area. So hence you could go for the deep coal seams. Secondly, we do know there's gold potential. So while you find that the Evander mines is currently mining to the north or to the south of our site, it is very viable that they can continue into the Leandre area. In addition to that, we then have the bushveld, as Lou mentioned. So we do have another lobe of the bushveld complex. I mean, the reason why we don't consider this is simply because there are like thousands of years of PGM reserves, so nobody wants to go to this area. Strictly speaking, we also want to consider a sort of a hub approach. Can you convert this government back? Can we stop looking at, mining and environment differently? Can we maybe say that here's a resource where you could possibly extract coal for the next 20 years, and then as you mine coal, coexist with the environment, convert that coal, pump the CO2 underground, utilize some of the CO2 to make the fertilizer material, rehabilitate the mine into an agricultural area, and also do deep-seated mining, for example, extracting the gold. These are all viable options. The other one that we mentioned, we spoke about the hydrogen. But these deep mine voids as well, or fractures, actually forms a viable place to store hydrogen as well. So we're looking at, this is a very niche, sustainable model. And I think maybe if I take it, these are young students as well. This is sort of where the future of geoscience is going. No longer we're dealing with what is a laser light and a Royal light, and a Dr. light. But we still need to know that because that suppresses the CO2 very much. But in addition to that, how do you then make a sustainable future? I think that's the important thing. And maybe the last point I'll make note is, do not forget the geopolitics of the world as well. We do need to look at how do we get more sustainable as well. And the true question is, how do you take our own natural resources and create a sustainable future for ourselves and the people of South Africa? And I think that's ultimately the long answer to this, but yes, we would want to continue mining the resources.
On that note, that very inspirational note, thank you so much, Taufeeq. That was a very expertly delivered, and I think a very optimistic message for geosciences in general about how we can contribute not only economically but socially to many aspects that many challenges we currently face. So thank you very much.
Thank you.